Here's the foundational parts of the math and physics. And hopefully that's running. See, my little 4-dimensional hypercube. You keep changing the observer point such that you can see it rotating, right? Here's my famous heroes, Rolf Landauer. Erasing information causes a loss of energy. It was in 61. He proposed that, and finally it was measured in 2014. John Wheeler said it from bit, since bit is the smallest change to a black hole. So bits are physical, and they have an effective energy, and they have effective mass. So you can ask the question, how heavy is a thought? Because it represents a bit, and those bits have an effective energy, and therefore they have an effective mass by E equals mc squared. So it's very subtle. It's very subtle energy. But I still wouldn't call it energy. I would call it bits. So reality is hyperdimensional. It's not 3-dimensional plus time dimensions. It's hyperdimensional. Bits, qubits, and e-bits are very real. They have essential behaviors, and they require a dimensional substring. A bit is a one-dimensional. It's used to make qubits and e-bits, and that's part of what I did for my dissertation. So a qubit is a quantum primitive for the superposition of 2 states, and an e-bit is 2 of those combined, so it creates 4 private dimensions. And Shor's algorithm is 2 to the 1,000 states, which is bigger than the number of particles in the known universe, and it's faster than any classical computer. So my belief is that these are the 3 foundational things. Information is physical, the reality is hyperdimensional, and it's based on these requirements that we've been feeding in her. And thoughts are information things, and intentions can affect the physical world, and thoughts can directly affect these devices, and they have to show how we can affect order. Okay? So this is kind of the building structure here. Each bit is orthogonal. So this is a bit. This is a representation of a bit. It has a heads and a tail. You can think of it as the state and 0 and state 1. Interesting about a bit, if you think of it as a coin, it's mutually exclusive. The head side of the coin and the tail side of the coin is mutually exclusive. And if you represented those as vectors and you were to add them together, they cancel. So if you take 2 states and you sum them together and they add to 0, that means they can't exist. That's mutual exclusion. We call that co-exclusion. And if you take 2 states and you make them so they're 90 degrees apart, this is spin 1/2, that's what a qubit is. It takes the 2 states of the heads and tails, like splitting a coin in half the hard way, and now making them orthogonal. So now you have the heads half of the coin and the tails half of the coin. Each has their own state vector. That's what a qubit is. Okay? And now you have a phase angle, so you can be half heads and half tails. That's where phase computing comes in quantum computing. And this phase is you can have 45 degrees, which looks like a perfectly balanced heads and tails when you run experiments with it. And a qubit, which is this, ABC, is actually 3-bit vectors, and the standard model comes from that. And then e-bits are 2 qubits together. It creates 4 dimensions. Again, all of this assumes they're not in space-time. Regular quantum computing always assumed all these things are embedded in space-time. It doesn't work. Yeah, they're very useful to predict things, but they're not embedded in space-time. They exist by their own private dimensions. Otherwise, e-bits wouldn't work. E-bits only look like they're non-local correlations because they have their own private dimensions. It looks non-local to us, but it's because they have their own private dimensions. So the reality of dimensions, not just mathematical, but the reality of these dimensions are really important. It turns out when you have, this is the kind of the hierarchy, this is Euler's it from bit. We're going from the smallest increment to the biggest increment. It turns out if you have greater than 20 bits, now you have content addressable memories. And these properties emerge that are very unintuitive. This is a symbolic representation down here in the corner. We're going to show a slide about that in a couple minutes. This is a probabilistic geometry. So each ball is a probability cloud. And you can show that properties emerge, like I was saying, the surface of this area of the black hole is the volume of the surface areas on the black hole. That's an unintuitive probabilistic geometry result from high-dimensional spaces. Same thing. By the way, I worked for 3 years in this probabilistic geometry and got patents on it, and that is where I got the $1 million grant to work on that. And the black holes are the biggest thing, and even empty space is formed out of this. When I say protophysics, I mean before physics. This is a picture they usually show the beginning of the universe. This is the Big Bang. And they call it the first singularity created, the Big Bang. Time itself was created. Space and inflation were created. The energy fields and the matter, gravity were all created. For this is our view of the... But what happened before the Big Bang? Well, there were still quantum states here, but there was no time or energy. So this becomes a bit bang, because those quantum states still existed. All those dimensions don't come as a result of the space that we are. They're more primitive. we have all these hyperdimensional states, or the quantum states, and some of them came together and helped form our universe. And our universe is a big simulator running inside this bigger hyperdimensional space formed by all the quantum dimensions. So it's a quantum version of the matrix. Okay? And so they are quantum bit states. They're highly specialized state. And this is like a big thought. And the question, who had the thought? You know, God says, I wonder what would happen if I did this and oops, the universe was created. You know, that's my joke, because God would be omniscient and he would know that that would happen, but that's my joke about God. So how do you get space and time emergent out of bits? This is part of the physics I did for my PhD. In 2002 is when I graduated. I was the ripe old age of 49 when I got my PhD. But basically you can say A is a bit vector, B is a bit vector, and if you add them together, that means the only thing that you can say they're orthogonal and orthonormal, the only thing you can do with two vectors like that is add them together. And so that means they're occurring simultaneously. So this abstract space and this abstract time, if they're occurring, this is space-like. So plus means space-like operator in the math. And likewise, if you have this state and then later you have this state, which means that they exclude each other, so this state plus that state equals 0. They cannot occur simultaneously. This is what a classical bit looks like. That means that if you saw this state and then later you saw this state, they can't occur simultaneously. That means some operator must have caused them to change. So that causes this local change, and it calls a time-like operator using multiplication. So this is how you can bootstrap space and time itself just from addition and multiplication. This is fundamental, and it's space-time and like time-like, which is what physics talks about from a relativity perspective. So here is the coin demo. A person stands with both hands behind his back. He opens his hand and shows a coin, and then hides it. Again, he puts out his hand and shows a coin, indistinguishable from the first. So the question is, how many coins do I have? Well, it represents one bit, right? Either I have one coin or I have more than one coin. You know there's at least one coin, but there could be two, right? So then I go to the next one and I say, the person now holds out a hand showing two identical coins. Right? So you just receive one bit of information, and from Landauer's principle, that information can't just be created. You have to account for the energy for that, right? But you have received a bit of information. So the question is, where did that bit of information come from? It comes from the simultaneous presence of two coins. We call that a co-occurrence. Okay? The simultaneous presence of two things is Landauer's principle. If you take two dimensions that were not together, and now they're working together, you just created information, which now has an effective energy to it. This is the energy of the Big Bang. When we were working on my PhD, we hadn't gotten to this, but 10 years later, my colleague and I, we wrote a paper out there. In fact, I have a YouTube video out there, I presented on this, that shows that when we actually analyze all the states from an information theoretic perspective, the coin demo comes out exactly one bit for this case. Not rounded, exactly one bit. So it says we predicted it should be that, and then when you measure it using the mathematics, it comes out exactly that way. So this is good news because we call this non-Shannon information, because Shannon never talked about this kind of information. He was always talking about channel capacity and token capacity. Okay? Simultaneous presence, though, is not something that he ever did. So there's all kinds of statistics, first of all. Realize that you have probabilities are intrinsic. Remember I said the spin 1/2? Probabilities are intrinsic. Okay? And what's interesting about that, either the probability is intrinsic in there, or somehow this object has global knowledge for all time in it. So you have to take your pick which one you prefer. So, but quantum states are statistical. And remember I talked about the Schrodinger's cat, the poor cat who's half alive and half dead. Quantum states can be in the state of superposition, but the question is, when does the superposition state stop? Do they stay only in the quantum level, or can you have a cat that's half alive and half dead? Because you haven't looked, so you don't know yet. So what scale does superposition end? They found out that it can go pretty big. They find that particles as big as buckyballs can be in two places, which is a pretty big thing. A buckyball is 60 carbon atoms. It's pretty big. And they're making micromechanical paddles that also can be in superposition. So we're just used to things not being in two places in the macroscopic world, but they're pretty big. The other thing is normally we think about classical statistics. The example is a pair of dice. There's 6 times 6, 36 possibilities, right? And you can count the number of times double one shows up is 1 out of 36. And so the number of times that you get pairs is 6 out of 36, 1/6. But if you use BoseEinstein statistics, it says if you have something that's an indistinguishable state, you have to only count it once. And Bose is from India, originally, and he made a contribution, which he told Einstein about, so that's why it has his name on it. And he showed that if you do this special way of counting in quantum mechanics, where you take two things that are indistinguishable, it means that if you had a pair of dice where you have 3 and 4, but you also had 4 and 3, those are indistinguishable. You can't tell them apart. So now instead of having 36 states, you only have 21 states. Which means now 6 out of 21, you have a much higher probability with Bose statistics to have a pair than if you had regular statistics. So if you would like to have Bose statistic dice if you went to Las Vegas, you get more pairs that way, okay? The point is, who ever thought there were different kinds of statistics? But Bell statistics are also different. If you take random things, you say, I'm only going to expect to see a correlation, randomness, it should only be 1/4 of the time. And then all of a sudden you entangled states and you're seeing more than 1/4 of the time. That's what's called Bell statistics. And it's because something is correlated beyond what it should be, and that's the non-local behavior that you see. Also, there's retrocausation statistics that look very much like Bell statistics. It says things are correlated that shouldn't be, and across time. Bell statistics are correlated across space. And also statistics and information and entropy are all related. Example, Maxwell's demon. Maxwell's demon is a little guy, he's sitting there and he's opening a little door, lets all the hot molecules to one side and all the cold molecules to the other side. So that's like getting free energy, because now you can use that energy to run a motor, right? So it seems like, well, that's hard, that shouldn't be done. Now they know that the measurement that the Maxwell's demon takes to measure the hot and cold exactly measures the amount of heat that he's pumping into the other side. So you can actually look at it from information. It took them 20 years to figure out why Maxwell's demon was the way it was, but now they understand it's from a measurement information perspective. Also, once you get to high-dimensional memories, we're going to show you that if you have a bunch of small vectors and you combine them together, just like we do in our cell phones, CDMA, they have 250 dimensions that are used in our phones. It's CDMA, code division multiple access. Essentially, each one is working on a code, and those codes look orthogonal even though it's in a higher dimensional space, right? So the small dimensions all look primitive, but the big vectors that are showing in the space is the way we communicate on that, okay? And so it turns out that math works really well for cell phones. It also works for the brain, and that's what CAMs are. We're going to talk about that a little bit more in a minute here, too. If you look at Shor's algorithm and you're trying to simulate it, you can't because you don't have a computer big enough. But it also requires infinite precision floating point numbers, which are also impossible. So you realize that somehow quantum computing is doing something really special if you're trying to simulate that and you don't have infinite precision. Probabilities is fundamental to this, and there's all kinds of probabilities in here. And realize that if you're not interested in probabilities, well, you should be, especially Bose statistics and Bell statistics and retrocausation statistics, and the fact that every quantum state is a probability. All of those things are fundamental. Like, for example, on this one here, it shows Boltzmann's statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. Notice the only difference between these things is they has no field here, a -1 here, and a +1 here. It shows the different statistics, and out of that comes spin 1 integer spin and spin 1/2. These are for bosons and these are for fermions. Fermions, they exclude each other. Bosons don't, and so this is the Bose-Einstein condensate. Einstein figured this out in the 20s after he interacted with Bose, that there should be this special state called Bose-Einstein condensate. And it wasn't until the 90s when they finally built it, 70 years later. This is fundamental, and so fundamental topology must create these rules of statistics. I showed you this once before. I'm going to draw again. One bit is a vector, a bit vector. It has 3 orientations, plus and minus, and 0. So it's actually a tri-state vector. It's like, it's like tri-state bus, where sometimes you can drive it once, sometimes you drive it 0, sometimes you're not driving it at all, okay? 0 means does not exist. These are orthonormal vectors. Each vector is like its own little dimension, and they're all orthogonal to all the rest of them, okay? co-occurrence generates, this is mutually exclusive, we call it a co-exclusion, but your co-occurrences generates information. We talked about that in the coin demo. So if you take two of those, you can create a qubit. So now each one of these has a plus and minus state, but we think of this as the head state, and this is the tail state, it's the two halves of the coin. We can symbolically represent it like this. In Hilbert space, it's represented like this, 2 dimensions, the 0 and 1 vector. But realize that in geometric algebra, if you have A and B, you also have this product AB, which imagine it's plane called AB with the vector that's orthogonal to that. So it's the right-hand rule. So it's like it's sticking out. So you create a three-dimensional space, but one of them is a bivector. This is spin 1/2. This is a spinner called a spinner. This turns out this AB has the exact same properties as an imaginary number. Its square root is -1. Which means you can use it as an operator. So geometric algebra, this is geometric algebra representation. If you have a spinner, and if you... So we've covered this a little bit here, so I can go a little bit slower, but the slides at the end are less dense. So the good news is we're about on time. So again, you have to look at how it's represented, and then if you take two of these qubits like this, now you have qubit 1 and qubit 2, and you put them together, you get what's called entangled. That's this 4-bit. I symbolically represent it like this, and this is the Bell operator and the Bell states. And what's interesting is our work 10 years after my PhD, we realized that this state is T sub I and this is T sub j, and if you take T sub I and T sub j and T sub k, that these things here, if you sum them up like as if they were quarks, you get the Higgs boson, and this is Higgs squared. So we believe this is the definition of the Higgs boson, and it's in 4 dimensions, so it's entangled. Well, no wonder they had such a hard time finding it, because it's entangled. We call these Tauquirnians, and it shows that you can represent a 3-dimensional space inside of a 4-dimensional space. We've also shown there's a Tauquinian. You can represent a 3-dimensional space inside a 5-dimensional space. And what do I mean by a Tauquirnian? Well, in physics, if you have a 3-dimensional space, a photon looks like this. It's 3 dimensions, A, B, and C. We call this a Q-trit. Likewise, if you take this bivector I just showed you here, you can take a plane, and the orientation for that plane is inside. So if you have 3 bivectors, it represents the same volume as 3 vectors. One is just a dual of each other. And likewise, you can take this and you can make something that looks like A and plus BC. It's just like one of these plus one of those. Then you get this, and we believe that's a quark. Okay? So what we found out, if you can do rotations in this geometric algebra, this is the geometric algebra 101 that I did my dissertation on, you can find out that you can create a dark quark version of it. That a quark has this structure, W plus XY, and we would call a dark quark is a 4-dimensional version of that, and it's a rotation of this Higgs, and it looks like this, W plus XYZ, and so a dark quark looks like this, and we know that 96% of all of the universe has to be dark energy and dark matter. And the reason is because it looks like a thing of jelly beans where there's all this dark, literally 96% of all of the universe is dark matter, otherwise galaxies wouldn't form. And they know this. It's known physics. That's how they know it's there, okay? Also, we found out if you take these 4 dark quarks like this, and since you're in a 4-dimensional space and you take the sum of these 4 quarks, you get what we call dark matter. And it has, some of these states are d squared is equal to 0, so it's a boson. So that's the dark energy state. So here you have dark matter, dark energy, and the Higgs all using the same math. And they're all entangled. No wonder we can't see it. It's all 4-dimensional. Oh, by the way, the neutrinos are 2-dimensional. No wonder we can't measure those either. Everything else is in 3 dimensions. Okay? This is the kind of stuff I've been doing over the last 10 years in my spare time. Okay? So if you take a particle in geometric algebra, remember I said everything is verb-noun balanced? So you can just take the states. It turns out in G1, which is 1 dimension, G2 is 2 dimension, G3 is the Q-trit, is 3 dimensions. If you take this formula right there that's on the screen in red, I can execute, that's a Python expression, you can execute it, and GA-solve iterates through all the permutations for the number of dimensions you pass it, and it finds that it tells you all the things where this is true, where x squared is equal to 1. And you find that dimensions themselves, the bit vector, is true. So it's like If it's something is x squared is equal to 1, means it's a particle. This means a bit is a particle. We just can't measure it. We have to build something the size of our solar system to measure it. Okay? So we've been saying bits are primitive. Well, it shows up right here. Okay? We also find that neutrinos are in there in G2. We also find out that in G3, you can find them, and you get the ones that are mirrored in the other case. You also find them, you find electrons are particles, and you find protons are there, and if you rotate this, you get the neutrons. If you multiply this equation times xyz, you get something that has 3 bivectors and 2 vectors, and that's the neutron. So you see all the primitive particles are showing up just by this little simple formula that I can do in my computer in less than 10 seconds. They just show up. Just due to topology. I don't have to build a particle accelerator to do this. Okay? Likewise, if I go into G4, I find something that looks like the mass carrier. Think of this as a graviton. It's a particle. And I find 16 more signatures. So there's particles up in G4. And by the way, this computation took me 1.5 to 2 weeks to run, because there's 43 million cases in here. For my dissertation, I was running proofs on 43 million things. Okay, and this takes some time to run. This stuff is instantaneous. This stuff takes a long time, and you'll see in a minute here. There's all kinds of properties you can get out of this, and there's a YouTube video with more details about all this if you want to see it. But I'm just saying, there's real math here, and I think there's even real physics here. And it can be done really easily once you have the right model for all of this, okay? Likewise, you can say, tell me all the things where x squared equals 0. That means it's nilpotent in that, which is the definition of a boson. And it turns out in G2, you find that there's the weak force bosons, W and Z. And if you go into G3, three-dimensional space, you find photons. This is a Q-trit, it's a photon. That's the definition of a photon in G3. It has 3 dimensions. If you rotate that, you get this. We call this quaternion, it's a rotation of the photon. Space itself is bosonic, which is interesting. I don't know what it means. And if you take 2 of these quarks together, by the way, quark looks like that, take 2 of those, that's also bosonic, and that's a meson. And this is a strong force gluon, which is the sum of the photon and the quaternions. So the thing is, bosons, once something is boson, if you take 2 bosons and multiply and add them together, they're still bosonic. Okay? So realize that this is all the kind of deep math and physics I've been doing over the last 10 years, 15 years. Well, actually the last 20 years, because I started my dissertation in 1997 or 98. And this is equivalent to Pauli algebra and Dirac algebra and things like that. We think this is the Higgs boson. And these are entangled states. And they could never represent this in regular vector notation because the operator is part of the state. They're not verb-noun balanced. So here you have these states that one of the components of the particle is the operator. And so you can't express that in matrix math. You can express it easily in geometric algebra. It says there's something fundamental wrong about matrix math for doing this kind of work. It also gives you a slightly different prediction for entangled states. Entangled states, they always say, well, it's a vector space. No, actually, it's a bivector space, and you get a different result if you assume one versus the other. So this is how they treat standard particles. This is the standard model right from Wikipedia, and up till 2 years ago, it just had these 16. And all of a sudden, poof, here comes the Higgs boson. By the way, there's another dozen or 2 dozen or 3 dozen particles that they're proposing out there that exist out there but hasn't gotten into the standard model. Everybody has a model that predicts new particles, including the gravitons and all kinds of things. Well, if you take a look at it from our perspective, you look at it based on the graded math, you have a bit, which is in G1, you have the primitives that are in Q2, in G2, and it's these. Oh, and it predicts there's a 4th neutrino. Why haven't they seen it? Because the 4th neutrino, they're talking about in some places, oh, they think there's a 4th neutrino, but they don't have any clue about what it is. Well, in this math, it shows up easily. You sum the neutrinos together, and you get another antineutrino. Or you sum up the 3 antineutrinos, and you get a new neutrino. Well, no wonder they can't see it, because they have to be able to produce it that way. Okay? So there's a prediction. But it looks like this. It looks really clean, and this is pretty clean, and it doesn't have any stray stuff off the side. This is just arbitrary, because they actually look at SU3 symmetry to predict all these states. But I think in G4, there's 17 new particles and 30 new bosons. The Higgs and the dark energy are part of those, and this whole space needs to be mapped out yet. So, if you're looking for new particles, it's either there, or it's the quaternion itself in G3, which is a bosonic state. Okay? We're making good progress. The hardest parts are done. This is the fundamental physics part. That was saying how bits bootstrap the universe and all the particles and everything we know. And we talked about how it can even bootstrap space and time, how it can bootstrap energy, and how it can bootstrap matter with these particles. We've kind of bootstrapped the universe. We just booted the universe. Okay? But now, once you get up to high dimensions, we have to understand about content-addressable memory. So this is content-addressable memories 101. Also known as Canerva memories, also known as sparse distributed coding, also known as correlathms, which is what I got the patents and the $1 million grant on. Pick a random point, P, in 3 dimensions. It's easy. Now pick a random point in 100-dimensional space. It's kind of hard. Hard for you to imagine how you pick a point. It's easy to do in Excel. Just create a column, create 100 points, and put a number in there that says random number between 0 and 1. And you can just create a 100-dimensional space with a random point in there, and that's all those vectors, okay? And it's just a random point, a random dimension here, a random dimension here, and a random dimension here. It's easy. You can do that for 100 dimensions. Now you can pick a second point, Q, and a third point in each space. You compute the distances between each of them. You find these distances, have an average value and a standard deviation. If you do this hundreds of times, you write a little program. It's hard to do that in Excel. You write a little program. You do this over and over again. What you do is get a plot that looks like this down here in the bottom. The plot says that if you compute the statistical distance between them using Euclidean distance, you'll get a distribution like this. But if you increase the dimensionality to 100 out here, or 1,000, that's 1,000, this is 100, you find out it has exactly the same shape, but since there's more dimensions in it, its distance is longer. So if you take that distance and you normalize it by the distance, you find out that the distance metric is the square root of n over 6. This number right here. This is for random numbers between 0 and 1. Okay? And that's the number. And you can prove that using Mathematica, that it's exact. It's not just an average. You can compute the average, but you can find that that's an exact answer. So you take any n-dimensional space and you compute the distance between 2 random points, you find it's that. And the standard deviation of that looks like it's the square root of 7 over 120, which is also exact, which is hard to believe. And it's independent of n. So if you compute the distance, you can't see it very well, PQ, the distance between the center point of the space and some random point P, and distance between another center point at the center point of this P and some other point Q, you find this distance the square root of n over 12, which we call the standard radius. Imagine that you have a sphere. All the points are a radius away. Well, this random space looks like they're all tetrahedrons. Every point is equal distance to all other points. So imagine it's like a bumpy star, a bumpy tetrahedron, high-dimensional tetrahedron, but there's a midpoint of that tetrahedron, just like there's a midpoint of a pyramid, and you can compute the radius if you know the midpoint of the space, which is easy to compute, or you know by definition it's just 0.5, 0.5, 0.5, and then you can say, what's that distance? And you can say square root of n over 12. And that standard deviation of that is also the square root of 1 over 60. And so you find out that for large n, the standard deviation, standard distance radiuses are constants based on the number on the n. And this is good because they're maximally far apart, which they don't run into each other, but they also have this property. They have this nice little property like this. This is the probabilistic geometry that I was talking to you about. So you randomly pick 2 points, P and Q, and here's the midpoint of the space, and this is the standard distance that we were measuring, and this is the standard radius that we were measuring. And if you take those and you compute all the other points, if this is standard radius, and you normalize by the standard radius, so this becomes sort of unit measure here, this radius here, you find that this becomes 1, this becomes the square root of 2, this becomes the square root of 3, this becomes the square root of 4, this becomes the square root of 6, this becomes the square root of 12. Which is pretty amazing. And what's interesting about that is if you take the standard radius on both sides like this and the standard distance like this, you find that that's this and this. You find out this angle is exactly 90 degrees. That means randomly selected points in a high-dimensional space are orthogonal, which is exactly how our cell phones work. Which means they reject each other. They're a perfect encoding representation for information so that they don't run into each other. And if things are similar because they have shared dimensions, then they're going to be closer together. But these are things for randomness which are as far away apart as they can be. So it turns out this is the representation that doesn't require matter, energy, space, or time. All it requires is primitive dimensions, which there's a lot of in the universe, bits. And it holistically generates these, what we call giant vectors, which you can compute this Euclidean distance from it, but it turns out it's not distance, it's a correlation. And you can find out that this standard radius becomes like the light year in physics. It's a standard measure of a distance, like a distance-like thing, which you can use to normalize everything. And you can find out, if you say, oh, it's 25 million miles, well, how big is that? Well, if you say it's 0.5 light years, it means something different, you know. You know what it means from a metric, no matter what your units are, everyone would be able to do that, okay? So these big thought vectors are built from these small vectors, and they're orthogonal. This is the mathematics of law of attraction. This is the same technology that the guy who founded Palm Pilot, Jeff Hawkins, he's working in a company called Numenta, and he basically says if you're not using sparse distributed coding technology, you're not doing AI. And he's doing it all in Python, and you can download it for free if you want it, and he's making an industry out of it, and he's doing this kind of neural computing. Okay? I'm not the only one that was working on this. He was doing it at the same time as we were, 15 years, but he had lots of money because he was wealthy. He sold Palm Pilot and made a lot of money. He's investing all his money in neural computing now. So here's the last piece on CAM, and then it's kind of downhill after that, which is good because it's getting 8:30, and I'm sure you're glazing over already. But remember I said you can take 100 random numbers between 0 and 1? You can also take 100 qubits, where the information is not whether it's a value between 0 and 1, it's a phase angle. You can use this technology with this kind of mathematics with any kind of space. By the way, you can also use it for looking how similar things are for Match.com. You can find out how similar or different you are using the same technology, looking at the characteristics, okay? If you have 100 qubits, and you pick randomly every one of them to be a phase between either 0 to 9 or 0 to 360, it doesn't make any difference. It's still a random phase. So which means you have uniform phase. You have the same number of points at every phase. Think of it as uniformly distributed through phase. Just like you have number between 0 and 1, you have just as many numbers at 0.7 as you do 0.3. You have just as many qubits at 45 degrees as you do 10 degrees. So it's uniformly distributed, okay? And if you do that, you can create an ensemble, and you can think about it as quantum computing. And you can take a bunch of those, two ensembles, A and B, each with 1,000 qubits, each with a random phase, and then you're going to store that random phase. And you can take two small a and small b ensembles, each with a random phase, but this is just a phase number. It's not a qubit, it's actually a phase. You just store it as a number. And then you remember all those, and if you measure big A with little a and big B with little b, it says measure this qubit with this phase angle, then you're measuring the distance versus the last time. And if you repeatedly do that, you'll find out that the last distance of A and the current distance of A is only 70% of this metric standard distance that we talked about. And if you compared A with B, you would find out it's standard distance away. So you can distinguish between A and B even though you don't know any of the phases. And the reason that works is that the things that are about 45 degree induce complete randomness, but things that are off the 45 induce less than random. So you're using random phase, and you don't care what the phase is, because no matter where it's at 45, it's okay. And if you shift everything by 90 degrees, it's still the same. They're still random phase and still uniform. Okay? And you get this plot here. And the more dimensions you have, the more discrimination. So you can imagine that you can distinguish between something that's here, a spike here, versus something that's a spike at standard distance. And that's why you see two clusters, like cluster 1 and cluster 2. This is what probabilistic computer looks like. It says you have a bunch of points that are probabilistically related to each other, near each other. They look like cluster 1. They're less than standard distance apart. And the things that are something else that's standard distance apart are farther away. Okay? So things naturally collect with each other that are more like each other. Okay? This is the mechanism for quantum mind interacting with the brain as an antenna. Because the brain looks like, in fact, this mathematics was created assuming that neurons are firing randomly. But for your brain, they're firing the same random. So when it talks to the quantum version of yourself, the higher dimension of yourself, it's using the same states in it repeatedly, and then it matches this mathematics. So you can see how this mathematics, in fact, this is the mathematics of the law of attraction. In fact, it's the only math that could possibly be the math for the law of attraction, because the only thing that naturally clusters like this, where the data becomes the address. So if you know anything about law of attraction, it says like attracts like, which means we need some meaning-based matching. But there is no meaning in physics. So how do you do that? So here's a mathematics that would support that. Okay? Like things are very near each other. It's just a high-dimensional version of the vortex. It's an inclusion-based. So the things that you want to include, you include those dimensions, and if you don't want to include them, you exclude them. And in fact, you can't push them away. So this is, remember when I say when we took two dimensions and we combined them, we got a bit? Well, essentially we're combining the dimensions we want and we're letting go of the dimensions we don't want. Okay? The address is equal to the data. So this is burden-bound balance too. Okay? And so massive contributions to the big, each of these small little things create the big thought vectors, and there are a whole bunch of neural correlates that feed this. But because you have this big vector space, if two things are near each other, they like have a phase angle. So you have quantum computing in the phase space with these big vectors instead of in the tiny vectors of quantum computing. So you have superposition in here, and so things that are naturally near each other aren't orthogonal, they're closer to each other. So all the concepts about your family, they're somehow all related to each other. And so you can have emotional superposition. You can use NLP techniques to change your emotional state. So you can see once you have a mathematical representation for content addressable memories, you see it actually matches exactly the requirements for law of attraction. In fact, there is no other math that does that. And that's why Jeff Hawkins is using sparse distributed coding techniques, which is what this is, content addressable memories, for the same reasons. Because if you're trying to get certain properties that are available in content addressable memories and high-dimensional mathematics, you can't simulate it using less dimensions. It's the same problem that you have with quantum mechanics. You can't simulate it in a lower number of dimensions. Law of attraction, there's a lot about law of attraction, but it's all about the emotional guidance scale. And the emotional guidance scale is, one of the things about the emotional guidance scale is one of the dominant things that go into the little components that form your big thought vector. So whatever emotional state you're in is encoding your memories as a dominant factor. If somebody's joyful all the time, then all of their memories are stored in an emotion of joy, and that's part of how they encode it. So if you've seen that movie Inside Out, where she had 5 emotions, and each one took the dominance, each memory had its own, it was encoded with one emotion, and she was joy. And then at the end of the movie, she realized she needed a balanced emotion. She had a little joy and a little sadness, and each of the emotions were balanced in there. And then, so essentially she, instead of having each emotion be its own personality, she was above it and had the superposition of those emotions and mixed them together and produced this super state that was a combination of all those emotional states. That's exactly the metaphor that we're trying to get at here. So that inside out is the exact same kind of idea here. This is in the metaphysical world, this is called parts work. Because you're taking all the parts of you and getting them to know each other, integrating them. And you use emotion as the primary way to do that. Everybody has an emotion where, like for me, it's the justice fighter. If I find injustice, then I get really hot and and I want to take action and stuff like that. Well, that's not normally me, but that subpart of me is its own emotional subpersonality, and I have to integrate it with my regular logical engineering mind because otherwise I'm like ignoring it. So eventually the whole me is all of my subparts, like the Inside Out movie. All of the emotions are working together as one big unit. And this is sort of a model where you can combine all those, and there's no limit to the complexity of how you can build. Pretty soon now you're an observer of your emotional states instead of being stuck in them, because you're actually the combination of all of them. And so this is a metaphor for that. And it's a mathematical metaphor, not just a metaphor, but it's mathematical. So also, once you do this, you start realizing every one of these thought vectors are orthogonal to each other. So you can add them all up together any way you want, and they're maximally parallel computing. So we think about thought as being sequential, but thought is this Gestalt parallel computing, and this mathematics would allow you to combine it arbitrarily. As long as you keep adding more dimensions, you can just creating bigger and bigger thought vectors, and they combine in parallel. And some of these transpersonal experiences, and I've had this when I was talking to the four-leaf clovers, I had a very lucid morning that morning, but afterwards I couldn't remember what order things happened in. I was outside of time, totally lucid, totally aware, having conversations with four-leaf clovers. And then when I tried to recall it later, I couldn't remember what order things happened in. So I was outside of sequential time, I was in parallel Gestalt time. That's supercomputing mind. That's the void. That's the nirvana. Okay? That's the touching the divine. So everybody should experience that sometime, but know that you're stepping out of time when you do that, okay? So that's important. I'm kind of winding down now, which is good, because you probably had enough. But we talked about pranas. It turns out prana and the chakras and auras, it turns out every one of these chakras here has an auric body associated with it, which I didn't know until recently. They're like tied one to one, and there's actually 7. Most of the time we think of 7, but there are also 7 auric bodies out here, and each one of these auric bodies you can think of as physical, emotional, mental for the physical, physical, emotional, mental for the spiritual. These are the 3 major categories in NLP. All NLP maps into these bodies as well. And this is called the bridge. It's the heart chakra. And the heart chakra is the one that most of us have shut down. And so if you can open your heart chakra, that actually activates the most emotion in your body, because that's where the emotion is. Even though this is the emotional body, your heart chakra is the thing that's keeping our emotion shut down. So I actually have meditation exercises I do with people, visualization, where I quickly do a visualization where we rapidly open all the chakras at once. And then all of a sudden you feel like what it feels like to be aware. It's kind of fun. And most of the time when people think about the chakras, they always show these symbols, and they show these colors, which are good. It's the Roy G. Biv of electrical engineering, and the rainbow, right? And so they always think about red being the lowest chakra, but they always call it the lowest frequency. Remember what I said about frequency? If you're using the word frequency, you shouldn't be. It's actually the lowest complexity. And once you see that, you go, yeah, it happens to be red. They show it red. But it's also the lowest complexity. It has the fewest petals. And this one has more petals. This one has more petals. So the better notion is it's higher vibrational, not frequency, because it has more complex states in it, and it has more complexity. It has more states. And so that is totally consistent. So when you're more aware, you're actually dealing with more complex states. And that's the metaphor, rather than frequency. By the way, these are 2 pictures that my sister took of her dogs. And this is a picture of the aura. This dog happens to be playing in the snow. Very peaceful dog, but you can see the aura around the picture of this dog. And this has just been taken the last couple of years. And this other picture here was another dog that she knew. And you can see these orbs. And orbs are like little independent consciousness that show up in pictures around the world. I know some friends who can pretty much call orbs and get them in her pictures all the time. And my sister can do that. My sister also does out-of-body experiences, so she's one of the special people that she has to live in this life like that, where she's attuned to this stuff. And she loves animals. And so these are real pictures, and they're real, and they show up on film. And another colleague who works with autistic children realized that in some places, these little orbs show up, that they're actually autistic children astral projecting over and interacting, and they can telepathically interact with these and find out who the children was and meet them. They might not all be autistic children, but the point is that if you are a hyper set of dimensions, how would it show up here? As a little ball of light, a little filament of light, but it's actually, it's like a miniature version of a black hole, because it's all these little dimensions and it happens to interact with our, it doesn't have enough mass to do anything except show up visibly in our world, but it's interacting with us, and people who can see auras can see this stuff. So realize they're out there and we just are blind to it. It's like bees can see ultraviolet, but we can't, right? So we're blind to those things, but other people can see those things. So this is what it looks like. The quantum matrix, what this was meant to be, is kind of hard to see with the light on, but the background here is the high dimensional foam of the universe. Okay, this part here. This is actually a map that shows all the known galaxies that we know about in the universe. So it's like a galaxy cluster map. So it's a representation of the entire universe. And our consciousness is like a point, an observer point in that space, knowing that it's actually in a high dimensional space. And so that's the mind's eye. And people can actually, travel the universe. They can go visit other planets. Just like the movie The Matrix, this is the quantum matrix. And your observer frame, you can pick which dimensions you look at. And in fact, in the books called Carlos Castaneda and his work, Carlos Castaneda, they talk about the assemblage point, and they can shift the assemblage point for the student and then change him to a different universe. So it's that same language. Shifting the dimensions that you include changes your reality. So we're almost done here. Source science, what does it all mean then? Well, reality is a hyperdimensional quantum matrix, bit vectors. It's the consistency substrate of all quantum mechanics too, because we can show that using geometric algebra that we can see this topology. It precedes space-time, frequency, energy, matter, and classical worlds emerge from it, and this infrastructure supports all of physics, quantum physics, and metaphysics. And the law of attraction is naturally part of this hyperdimensional space through the content addressable memories. And similarities naturally form clusters near each other. All thoughts are these big vectors in there, they naturally cluster, which is, by the way, if you have two vectors and you randomly pick them, they're standard distance apart. So the information content of those vectors is 0 because it's like random numbers. But if you have 2 points that are near each other, it would be like if you had this wall full of bullseyes and you had somebody with their blindfold throwing darts at the wall, right? And then you looked at it and you would very rarely see any 2 darts on the same bullseye, and even in the same little, in the same target even. But if you had somebody do this and then you open your eyes and found 5 tightly bound things right in a bullseye in one of these targets and nowhere else, you think, well, that's something special, and the information highly unlikely from a probability perspective. So the fact that 2 points are near each other, you can show has an information content to it. You can assign a probability and an information content because of this standard distance metric. So there's another kind of probability that has information content, and that's the clustering of negentropy. And it happens without matter or energy. It just has to do with things that happen to be near each other get clustered near each other. So that's another kind of thing. So the mind is native to this, and all this other stuff feeds it. So here's my predictions for source science. Here are the technology, devices, techniques that could be developed. We could build training wheels to help people release from our brains. Lucid dreaming, remote viewing, OBEs. And by the way, you can do all that stuff now. There's all classes to take for all of this stuff. You can have telepathy answers. You can go take classes from Susie Miller, or you can train to be telepathic. Direct access, intuition, knowing, so we're less reliant on the internet. If we directly knew things, we wouldn't have to rely on the internet, because it's just a metaphor what we can do in our mind already. If we had direct experience of the divine and know we are connected, you really probably wouldn't have any religions, and there are probably, if you all know we're connected, it's like if you hurt your neighbor, you're hurting yourself. It's just a natural philosophy of the fact that there is no distance. Separation is an illusion. We're all connected. There is no distance. We could significantly increase our intelligences, emotional, mental, spiritual. You can call it ascension technology, but we wouldn't have to ascend to do that. We could build high-gain PK devices, I'd call them e-brains, and then we could learn to control them. We do that with our brain right now, if you believe that our brain and mind are separate. So let's go build a device and prove it. I believe we can. They have low-gain PK devices already. Let's build a high-gain version of it, use biofeedback techniques. Then you could walk up to any device and not even be near it. You could interact with it anywhere with your thoughts. You could have calming state generators. You could have these intentional host devices, and you could change the emotional landscape of mankind. You could have truly effective and approved healing techniques. I'm not saying FDA approved, I'm just saying they're effective, and so they're approved, and technologies. And the standard medical community is as much of the people who are the naysayers about it. And since this hyperdimensional reality exists independent, I mean, it really is a multiverse out there. We could have multiple universes out there. And so we could have interactions with more advanced aware beings. Even our higher self is advanced. Our consciousness is the tip of the iceberg of who our really consciousness is. But also I would call angels or spirit guides or even aliens. You can imagine that there's hyperdimensional aliens out there that in either different universes, physical universe, our physical universe, or non-physical versions of our universe. And they would all be much more advanced aware than us, and they would all be using that technology, because that's the basis of the universe. It's just like we all know what the speed of light is no matter where you are in the universe. If this was the basis of the universe, these hyperdimensional realities, then everybody would be using the same technology. And I can imagine that it would be unbelievably advanced technology. It's not that we can't think of it, it's not unthinkable, because the science fiction writers tap into that all the time, but it's unbelievably advanced, and it would make the last 150 years progress that we've seen seem prehistoric compared to that. So I think what you have to do is you have to get acceptance of source science ideas, funding research and development, and it's the acceptance of the ideas that will lead to the funding research and development. But I think the time is now. And so here's the big picture. Anita Girani says we're magnificent spiritual beings having a physical experience. And the source and mind is the source code of the universe. Source, mind, soul is outside of brain, space, and time. We are more than our physical bodies. We are all one. Unity in panoramic time. We are outside of time. The source and prana is real, unobservable, intelligent, and knowing. The source represents profound joy and love. Source is love. So as a scientist, I'm still curious about that one. I don't know how to talk about source is love. But if you have meaning, then you can start talking about it. But without meaning, you don't even have a chance to discuss what that is, okay? I'd say love is part of meaning. So if we can get to study meaning, then we can study potentially what love is. And so source is God stuff. So we are source, we are angels, we are God, I am. So you can see as, from a philosophy perspective, in any culture, as soon as you touch the divine and you step out of space-time and you have absolute awareness of everything, you know you're part of God because you have the same awareness of God does. And so the only state you are in that is that I am. It's the beingness. So it's not philosophical, it's a way of describing as best in language we can about what's almost indescribable of this hyper-aware state. And like I said, that Anita's book is very descriptive about those things. If you're interested in people talking about transpersonal states of awareness, she does a very good job in talking about it, and so does Eben Alexander. So we are spiritual beings. I said it was kind of getting light at the end here. We are spiritual beings more than our body. So the traditional view of physics says, hey, we're this machine, meat machine, but really this view of our mind and reality, it's like we're more than our physical body, and we're just borrowing this body. And in fact, we're running all of our parallel lives simultaneously. When you have a near-death experience, you step out of time and you have a life review. But you can see all of your life reviews for all time, not because you have instant awareness, you've stepped out of time. And you're still looking at it sequentially, so you think of it as a sequential thing, but it's panoramic time. I call it panoramic time. It's like being above the Grand Canyon. You see the whole river. It's quite a view. Well, when you step out of time, you see all of time. Some spiritual people have a time for this, they call it eviternity. A-E-V, eternity, eviternity. It stands for the time of angels. It's the time between human time and God's time, which is no time. It's sort of somewhere in between. And so there's all these transpersonal states that there are people trying to explain all the time, but they didn't have any way of talking about it except as an experience. So that's it. I said light at the end, questions and answers, and thanks for your time. I appreciate you all showing up here. And this took almost 2 hours. Was that interesting? And you can see there's actually a lot of physics and math, and sorry I bored you with that. But it's been my life for the last 20 years, which is why it's so compelling to me. So anyone have any questions?
Commercial viability and why energy is still being stored and all these questions comes up.
Yeah. Well, there is a huge industry out there of people who are doing healing. You know, the healer that I work with and the chiropractor I work with, they're helping people every day. I met a guy who was a Starbucks barista. He could see auras. He knew that I was doing a quick balancing technique on the cashier because she was so out of it, so scattered. I said, try this, and quick 20-second balancing technique. And then I walked over to get my coffee, and he says, did you just do a balancing on her? I said, yeah, how did you know? And he says, I could see it. I could see her energy pattern change. So we became best friends because those people are hiding in plain sight. And everybody has this ability. We just have to be awaken it in ourselves. In fact, I have an article I wrote a year ago out on the Science and Spirit magazine site, and it's linked from my site, my Quantum Doug site, and it says, awaken the superpowers in you, and it's a short, sassy little article. It says, hey, all these superpowers that we have are related to quantum mechanics, and go awaken it in yourself, you know. So don't be shy, you know. And so I felt good about getting that article out there. And so there's a bunch to learn, and there's a bunch to unlearn, because our view of reality is we have to unlearn it. And so children are the best people because they haven't learned it yet. So if you can convince your children about this as reality, have them go bend some spoons or whatever and realize that they don't have the predispositions that we have. The children, you know, it's like the autistic children. If you go read some of Susie's work, it's amazing. They say they're the advanced guard for the next generation of advanced humans. So, you know, we want to take care of the autistic children because they're our advanced humans, just being come into the world. So we can actually stop the recording if we want to, and we can just talk, you know. If somebody has questions, we can go on the board and we can be done with this, you know, we can be done with the talk part of it. Last time I did this, we talked for an hour in the meeting, and then they kicked us out of the meeting room, and then we talked for an hour out on the street. So, you know, it just kept going on and on because people were so curious. So I'm happy to do that. I'm going to stop the recording now, and we can talk some more if we need to.